Good. Okay, now we're recording. Okay, let's start. We're starting 3.7. And so what I would like to do is I'm going to zoom in. Let's see if I can zoom in. Oh yeah. So notice what we've done is we've done the rules for derivatives. We found out what it was in chapter 3, and then we got to 3.6, rules of logs. So the rest of it, chapters 3 and all of chapter 4, is really applications of derivatives. There's a lot of these. I think I'm going to skip just kind of a few here and there just so we can keep on still going schedule wise with things here. But shall we note here, we're going to finish off the rest of chapter 3, and we'll do that with rates of change. And look at it. Sometimes we think of calculus as not being in the natural sciences, right? Sociology, history, but we're going to look at some applications there. And social sciences here, sorry, natural and social. Okay, but real quick here, application. And then this book does something weird. In 3.11, it does hyperbolic functions, which is really just not applications. It's like, hey, this is one last functions you guys need to know derivatives of. So all of a sudden this kind of pops in out of nowhere. So we'll kind of keep that for the last one. Funny thing is they're trig functions here and they're hyperbolic. What in the world does that mean? We'll see. Okay, with that said, are we good? So this is from your textbook. We're just going to go over the problem itself. It's on page 221. If you, let's see, if you have your textbook with you, if you want to grab one and share, Huey. We're going to go through the problems themselves. They are complicated. Okay, this is application questions, right? So what happens with students, they can usually do the rules pretty well, right? Like derivative rules, right? Sine is cosine. Yeah, let's keep on going, right? Now we are required to think quite a bit more deeply into this here. So you can follow along with the book. That's fine. I just want to go over this little piece right here because there's a homework question like it. So we'll do that. So let's see, however you want to follow along, we're just going to do pieces of this just to get us going. Oh yeah. Okay. Oh gosh, which should we do here? So find the velocity, that would be one thing, I guess. Then we're going to do when the particle's at rest. So let's do A. Let's do A and C, just so we can get through some of these problems. I'll let you guys read the rest here. Let's see. And E, we're going to draw the diagram. So A, C, and E. We're good. That's the ones we'll do in class. I'll run through the rest of them really quick here, but the ones we're going to focus on is that one. We're going to go from there. And we'll talk about the slowing down and speeding up process. Okay. It's a fun little section. Okay, so let's go with position of a particle. So this is the way in mathematics we think about physics. So this is kind of a weird setup. You guys are in physics class, so again, you get the math perspective from physics here. So position, S is good. Is S usually position in physics?
Yeah, we use S or X.
Okay, perfect. So because of its time, so it's a function determined by time, it's t cubed minus 6x squared plus 9t. Perfect. That's the position of my particle, whatever this particle is that's moving. Okay, we are measured in seconds and S is measured in meters. Let's go for it. Find velocity. What should we do? Take the derivative. That's it. So here's my original function. Let's take that derivative. And I'm going to put it in different notations if you guys like. This would be the different notations we would use following Zechariah. And so V of t, we can just start writing that down if we like. Since S does not have a variable next to it, then it's going to be the ds over dt. Or because it's a function, We can write f prime of t. All of those are just fine. Cool. All right. Okay, we're gonna quickly do B, but you guys don't need to write it down. So it says find velocity after 2 seconds. And after 4 seconds. That's pretty easy. We're just gonna plug in the values, right? And so what happens is this little bar right here, it means evaluated at. So it becomes this little bar of what we plug in. So that's easy. You guys can do that. That's calculus student stuff. And so voila. So whoa, hold on. We have a value of -3 meters per second. What in the world? Go ahead.
Does that just mean direction?
Velocity is speed and direction, right? So to make things plain in mathematics, we either are going to the right or to the left. That's kind of our trajectory. So -3 meters per second, that means we're going left. So let's go with plugging in a 4. That means we're going 9 meters per second. Now we're going to the right. Okay, so whatever notes you want to put in there for those, since you guys will have those. So either going to the right or to the left. Okay, let's jam. C. What we need to do is we need to find when is the particle at rest? Now talk to me. What should we do there? All right, let's see. When a particle's at rest, it's not moving forward, not moving backwards, it's at 0, right? So a particle at rest just means the derivative or the velocity is set equal to 0. And we may have to do some factoring processes here. So please guide me through this here.
You subtract 9 from both sides.
Ooh, I was thinking actually factoring out of 3. If you subtract 9, let's see, then we're stuck with, but I got it in trinomial form already. I'm thinking I'm ready to factor already. I have it set equal to 0. So if I factor out of 3, that should make things a lot easier to factor with. Also thinking, let's see, I can divide out the 3. I can keep the 3 as a multiplier, whatever. It doesn't matter to me. But I think it's gonna factor into a -1, -3. That's the only way to make a +3 add to -4. Sweet. Cool. So I got myself, looks like 3 seconds and 1 second. Is that right? 3 seconds and 1 second. Okay, good there. So velocity equals 0. That's when we find out when the particle's at rest. Cool. Okay, speed through the other ones here. When do we know it's moving forward in the positive direction? When do we know it's moving backwards? We're gonna do this one really quick here. So if we do this here, we have 1 and we have 3. Is that right? Actually, no, let's do this one. Let's do D, because this is first time that we actually get a value of, change it on you guys, sorry. So what I have here is I have a timeline. Notice it's not going in both directions. It's only going in one direction. Time equals 0 is the starting point. So it's a ray as opposed to a line. And this all in terms of time. So it looks like I have this situation happening. I have t is equal to 0, it starts, right? t is equal to 1, we know it changes direction there. Could possibly, at least it stops, right? It doesn't have to necessarily change direction, right? So a particle can slow down and stop and then just keep on going the same direction. So that's a little tricky part. So now we have to figure out in between there, is the velocity positive or negative? So we have to pick some test points. So I'm going to pick a little test point called 1.5. And if you have your calculators, can you punch in a 0.5 into the velocity function? I need to see if it is going positive or negative. We don't care about the number itself. Who cares, right? We just care about the sign.
It's going right.
It's going right. Okay. And then I think we have answers for this one. 2 and 4, we have answers for already. I think 2 is negative, right? 4 is positive. Okay, so we can fill in these little pieces here. 2 is negative, 4 was positive, and 1/2. Yeah, plug it in, and we get ourselves a positive value. I don't even care what that is, but there it is. So my object or my particle started off going to the right. It went to the left for a little while, then it changed direction again, went to the right again. Cool. Okay. D is what we want to graph. Don't need to write that stuff down. Just the fact that we've made this little chart based upon the numbers. Okay, so now let's graph this guy here. So the graphing aspect. Okay, I'm going to start off like this here. So t is equal to 0. We can even erase this little piece right here even, because it does not. And you guys talk to me, is the position 0 as well? So we have time, right, and position at the same time. All right, let's see, and whenever we get S values, we're going to plug that into the original equation, correct? Because that gives us S. So if I plug in 0 into the original equation, notice all of the values or all of the terms have T inside them. So that should give me a 0. We're good. And please ask the questions. We're good. If I were to plug in a T equals 1 into my original equation, I should get S equals 4. That's kind of easy to do. Okay, so really, here we go. Our little dot starts off and we have little arrows saying it's going to keep on going to the right, and then we sort of curve it. Again, have you ever seen that in physics before? Okay. So when we hit t is equal to 1, let me go back to the chart real quick here just to make sure. Let's see if this makes sense. Let me go back to this little chart. It's positive, positive all the way till 1, correct? It's negative, negative all the way to 3, and then it's positive, positive for the rest of the time. Okay. So we have ourselves. So the next one that we're going to figure out is t is equal to 3. And you guys plug in a 3 into the original function. I want to know where I'm at. Because that dot will tell me. Let's see a few little things to add to this here. This is funky. I think this is like a funky way of doing it here. So we should put arrows over here at the end, guys. Real quick. I'm going to add a few little things. And this is actually in terms of S. It's a position graph, not a time graph. Time is we're just using it in order to determine where we're at. So before we put in a dot, I guess, before we put in arrows backwards here, we've got to plug in a t is equal to 3 original function, give me S. I think it's 0 as well. Absolutely. So the little dot here on the position. So if it was at t is equal to 2, right, we would put our dot right here. Right? But because we have s is equal to 0, we put our dot back in the beginning. So I don't know what happened here. This object, if we flip the positive negative around to up and down, right? So this object went up for a little while, hit the ground maybe and again, right? And then took off, which is it bounces again. If it was object hitting another object, maybe something, a ball hits the side and bounces back off or something, right? And then our initial position is all the way back here. Okay, so we got s equals 0. We can line them up like this. These two lined up again perfectly. And then I'm going to do that right here. And no dot anymore because we've never hit a 0, right? The particles never at rest again. Okay, yep. Want to show you that because it's very different from physics that we normally do. We'll get to those. We'll get to those as related rates. We'll get to those a little bit later. Okay. Jan and F, don't need to write it down. Just kind of think with me here. This is and the total distance traveled. So here it is, from 0 to 1, how much do we travel? Think about it, we went off from 4 to 0, is that right? Our S position, you can think about it, you can do it this way, it's formally. You can also look at the graph. Let's look at the graph. We went from 0 to 4, so we covered 4 units of space. What happened when we went from 1 to 3? Absolutely. So we went negative direction, yet we still covered 4 units of space, right? Because distance traveled, distance is never negative. Cool. Okay, so then we turn back around. Now we get to figure this one out. So f of 5 we don't know yet. Never computed that before, but if you put in 5 into the original function, you get 20. And so it traveled 20 units from 3 to 5 units. And how about 28? What are we in meters? I think we were in meters. So then you think about average velocity of this object, right? Even though it's switched direction, we can still think of average velocity. During the time, we can think of instantaneous velocity, which we did over here, right? We have a lot of things to sort of put together and think about. 1, 2, okay. One more thing I want to show you from the textbook here, which is this little, there's a G function here. Find acceleration. We should talk about this one here. Acceleration is then the second derivative of position, or we can say derivative of velocity, right? Okay, we good. Take derivative of velocity. I think we should have 6t minus 12. Is that right? If we look at the velocity function. That's cool. And if we wanted to finish it off, we plug in the 4 that we wanted to see there, and then you're all good there. Okay, all the different ways you do it. So a of 4, you have this little bar line. This is evaluated at t is equal to 4, or you plug it into the function itself. Okay, anyways, that should give us 12. It's 24 minus 12 is 12. Okay, and this would be meters per second squared, right? Because of the way we look at acceleration. Okay. Are we good there? Okay. I thought this was a cool little graph here. I think I regraphed it in Desmos. So I think it's that. I don't think it's clipped from the textbook. Maybe it is. Yeah, I regraphed it. Okay. I thought this was so cool. So, first things first, quick story, of course. So when I graduated with my bachelor's degree in math, I went to a job fair, and one of the people there was the Air Force. And what they were doing is they were launching rockets out of Lancaster, and they had this right here. They pretty much had graphs, and they would say, okay, this is what the rocket did. And then the interviewee, me, you'd have to tell them what was happening with the rocket based upon your position graph, velocity graph, and acceleration graph. So in this case, we have something went forward for a while, is that right? They went backwards for this time. Now notice the x-axis is in terms of time, right? It's the time graph now, so we have to change this up here. And then it goes forward from now on. And then we have velocity. Okay, so let's talk about this here. So velocity is positive, but acceleration is negative. What's happening during this time? This guy is slowing down during this time.
So are you looking at the blue one?
I'm looking at all of them. Oh, let's see which one's the blue one is our position function.
Okay.
No, let's see, no, red should be position function because it's a cubic. So it was at s equals 0 here. So the red one is your position function. Blue is your velocity, because velocity hits 0, that means we stopped movement, right? Then you have acceleration right here. Acceleration negative. Oh, sorry, green. Green is acceleration, right? So green is all the way negative over here. So this object, I'm not sure what was happening to it. Initially, it's going a certain speed already. So it did not start at rest like, hey, let me get going. This thing was already flying. And so velocity is positive. So it's going in the right direction, correct? But acceleration is negative, it's slowing down. Then it hits this little piece right here. Then it's going to the negative direction. Velocity is negative, acceleration is negative, which means it's speeding up in the negative direction. We're good. Then you have, again, the disjointment in regards to velocity and acceleration. It's going in the negative direction, but the acceleration is positive, which means it's slowing down. So right at 2, looks like right at 2, we had that little change there. And then we go the other way here. So as soon as these guys are the same direction, that means it's speeding up. We're good. So velocity and acceleration, just the sign of them gets us down. So real quick there, let me go back over here. So if we go back to this graph that we made, right? We have this guy's going full speed. It's slowing down, slowing down, slowing down, slowing down, slowing down, changes direction, speeds up for half the time. So somewhere here, right? Speeding up, and then so it's slowing down to change that. And then from here on out, then speeding up for the rest of the time. So we actually even have almost like what we could think about force in a sense right here, right? Speeding up, slowing down at that point. Anyways, cool. We're good there. That was a cool graph here. Okay. I think this is my problem now. This is not from the textbook. This is you guys to do. So if a ball is thrown vertically upwards in velocity, 80 feet per second, when its height, t's after position is given this, tell me what's the maximum height reached by the ball? Tell me what is the velocity of the ball when it is 96 feet above the ground on its way up, and then tell me how fast is it going when it's on its way down. All yours. Talk to each other.
Maybe zoom in.
Zoom in, absolutely. Is that way better?
Yes.
Cool. I like way better. Okay, so go for it. A physics problem. This is going to be something similar to what the homework is like. But I want to do the first one because first one is just so different. And again, talk to each other if you need to about it here. We got to the physics stuff. Okay, so I will give you guys a homework sheet. I'll see you guys a homework sheet tonight as well. So what's the maximum height reached by the ball? Anybody? 100. Let's go with it here. So maximum height. Is it equal to 0? Is that right? Divide by t. So I'm thinking that's when it happens. That makes sense. So it took 2.5 seconds for it to climb up. So see if this makes sense here. So position function, we took the derivative. We set the derivative equal to 0 because that's when you have a change of direction. You know the ball went up into the sky, right? And changed direction and when it started to go down. So that little change in direction right there, that was 0. Velocity was 0. When does that happen? It happens when it's 2.5 seconds in. That's cool. So once I know what that is, let's go with plug in 2.5 back into my original equation. I plug in 2.5 back to the original equation. Don't forget the square on there. I get myself 100 feet. It went 100 feet high. What do you guys say? That's pretty high or no? That's pretty high. 100 feet up in the air. And the ball's thrown. What an arm. Okay, then all yours then. What's the velocity of the ball when it is 96 feet above the ground as it's going up? What's the velocity of the ball as it 96 feet above the ground on its way down? So just trying to get you guys used to also, like, when are you looking about for the kind of like the X value or the Y value? What are you trying to find when? That's a major thing to sort of consider. Cool. Okay, so you guys talk to me first as a for B. Are we all ready for B? Okay. So how would you find out, like, what's the velocity of the ball when it is 96 feet above the ground? So how would you find that? What do you need to know in order to make that happen? Now we're trying to find V of t, right? Trying to find V of t. So we actually need the t in order to find out what the V is, right? So we need to know the time. At what time is the ball going up instantaneously at 96 feet above the ground? I need the time that it happens. So I think we're gonna do. So I'm gonna just write it up here, see if this makes sense. I'm gonna set the original function set equal to 96, right? Because that's what I need to find out for t. I'm gonna set the original function. We have some work ahead of us here because now we have to factor this guy down. Craziness. I'm so glad that 16 goes into all those numbers. So we factor out a 16. Actually, no, let's see. Let's multiply through by -1 first, then factor out the 16. I think you guys can factor this guy down.
It's, I think t minus 2 times t minus 3.
T minus 2, t minus 3. Perfect. So then that means at time equals to 2 seconds. Is that right? And 3 seconds. So think about what's happening physically to this ball, right? So it looks like it's going up. That's right, real quick here. Where's the position of the ball initially?
On the person's hand.
Yeah, person's hand. It's not elevated above the hand yet. So it is thrown at 2 seconds later. It's 96 feet above the ground. What happens at 2.5 seconds? Right, so boom, hits, wind, goes up 2 seconds, it's 96 feet high, right? 2.5 seconds later, it's at 100 feet, right? But it reaches its max, right? So then we have half a second later, now it's going down. It's at 96 feet again, and then eventually hit the ground sometime. So I got my t value when 96 happens. Therefore, if I plug in the 2 into my velocity function, I am good. Okay, and does that make sense? The 60 feet per second makes sense. Yeah, it's positive. The ball is still going up. That's cool. That's what I needed. All right, is this closer to a physics problem? Have you guys done something like this in physics?
Kind of. It's not as much about derivatives though, because we're just given that equations and then asked to plug in and switch around.
Perfect. Yeah. So if you guys will find out when you guys take physics in college, right? There's a calculus-based physics, and then there's non-calculus-based physics, and that's the difference between the two. So at calculus-based physics, you're looking at motion from a derivative point of view, looking at total amount of work. that was needed from a antiderivative point of view, or integration as we get there. So pretty cool stuff. Okay, I wanted to cover all the physics stuff today for sure. And there's our little ball, 96 seconds here, and then comes back down. Looks like 5 seconds. It's gonna hit, it's a parabola, right? So if it's a parabola, it has to hit a top halfway in the middle, right? 2.5, and then it's symmetric, so it's gonna hit the 0 to 5. Okay, what I wanna do is before next time, since we have some time, not gonna get to here, but we are gonna look at this here. So business and economic applications. So totally different understanding of things, but that's okay. We'll get there. Let's take the time just to write down all the variables so we don't have to do it next time. So business and econ applications. This is cool. What do we think of these? So X is going to be the number of units sold or whatever. Little p is the price per unit that was sold. Capital R is total revenue. Capital C is total cost. And then when you put a bar line on top of C, what happens here? It becomes the average cost. P is total profits, so capital P now, total profits. And then when revenue is equal to the cost exactly, we call it a break-even point. So let me just check something out. Okay. All right, and the formulas that we're going to use. So 4 formulas to start off with here. Revenue is, whenever we get revenue of things, it's always the how many units you sold at the price that you sold it at. So it's X times P. The cost equation, the total cost equation, has pieces inside it here, but usually has a constant variable. So A, in this case, the book wants to write A as the first one. Don't like it that way, but that's the way the book does it. All right, so R is equal to X sub T on this side. Here's our 4 formulas that we're going to use. A cost. Where does a cost equation come from? It comes from, we have to have a constant figure here because that's called overhead cost or fixed cost. If you rent a building for $1,000 a month, that is on you, right? No matter how much you produce, you're still going to pay that $1,000 a month for the lease in the building. And then we have things that are associated with X, X squared and X cubed. Those are called production costs. And now, as you produce more, you are going to have a cost associated with how much units you made. Okay, the formula for average cost is how much it cost you divided by how many units you made. There's your average cost. And your profit. How do we calculate profit? It's just going to be your revenue, subtract your cost, and it gets you your profit. Okay, so 4 formulas that we'll use as we go through a piece there. One second, let me just look up something real quickly here. And that was the sorry. There, okay, sorry, my mouse was going crazy. Okay, so we got that. We haven't got to something called marginal cost yet, as we're going to think about that, but we will do that next time.